Any questions? Okay, if there's no questions, let's go jump into the quiz. Okay, so here's our quiz. And the question number 1 was find the interval of convergence of this series. And be sure to state the test you're using. You just pop in the series. Okay, so to find the interval of convergence, I don't know if you remember, but hopefully you did. There's a 3-step process. What's the first step to find the interval of convergence? If you remember,
is it to apply the ratio test?
Yeah, it's a ratio test. So we're going to apply the ratio test. So let's start there. So it's going to be ratio test. And for the ratio test, what that tells us is we need to take a limit of the ratio. So I'm just going to start here and adjust. I'm going to take a limit. And as I mentioned in this class, if I don't say so, lim always means limit as n goes to infinity, because that's all we're doing. For this, these 2 chapters. And then the ratio test, you take the n plus first term divided by the nth term. So let's do that. So I'm going to turn that n to an n plus 1. And I'm going to turn this n to an n plus 1. And then remember, dividing it by the term with an n in it is the same as multiplying by the reciprocal. So I'm going to write that as 5n plus 2 over x minus 3 to the nth power. And then what I really need absolutely is I need some absolute values. I could do it here. Oh yeah, makes me do this. There we go. Okay, and what I can do next is I can rearrange. And rearrange, I can copy paste. And then what I'm going to do is I'm going to put the x minus 3 to the n at the left over here, and the 5n plus 1 plus 2 there. And that's standard with the ratio test. You always want to put terms where they belong. And then I have to get rid of that guy. Any questions so far? Okay, what's x minus 3 to the n plus 1 over x minus 3 to the n?
Minus 3 to the power of 1. So x minus 3. Or
just x minus 3. Okay, and note that the x minus 3 is in absolute values. So that stays in absolute value. Okay, we have these absolute values. So what we can do, let me save this guy and then go to the next line. Is now we can simplify a bit. And again, these x minus 3's go away. And you just get absolute value of x minus 3. And this becomes 5n plus 7. What's the limit as n goes to infinity of 5n plus 2 or 5n plus 7?
1.
Yeah, so we just get the absolute value of x minus 3. And remember, we're doing the ratio test. And when you're doing the ratio test, what are we interested in when we've taken our limit? Yeah, we want it to be less than 1 for it to converge. Okay, so any questions on that? And I left out an equal sign. Any questions at all so far? Okay, for what values of x do I get this absolute value less than 1? And there's two different values.
Four and yeah, 4 and
4 and 2.
2.
2 and 4.
Yeah, 2 and
Okay.
4.
So we can say is that so far we have 2 to 4 converges. Okay, and absolute value, it converges absolutely, by the way. Ratio test gives you absolute conversion. Okay, any questions so far? In fact, I think I'm going to just write that. That was step 1. Step 2, I found that I think it helps to have an organization and to realize this is a 3-step process and go through each of the steps, because this interval of convergence is important. It comes up a lot. All right, so now what's step 2? Step 2, though, is to test the left endpoint. Okay, so test the value x is equal to 2. So now what I'm going to do is I'm going to plug in 2. And when I do so, 2 minus 3, I hope you can all do that in your sleep, is -1. All right, what test is going to work on this one? Yeah, this is going to be the alternating series test. So note that 1 over 5n plus 2. I can say limit of 1 over 5n plus 2 goes to 0. Okay, any questions on that? We have an alternating series. We know the limit goes to 0, and it's definitely monotonic. And it is monotonic. So what is the conclusion? By the AST, what can we conclude? Yeah, it converges at x equals 2. What's step 3?
Test the right endpoint.
Yep, we test the right endpoint. So test the value x equals 4. And again, let's just pop that, copy it, and plug in 4. So to plug in 4, hopefully you can all do 4 minus 3 in your sleep. You get 1, and then 1 to the n is just 1. That just becomes a 1 over 5n plus 2. Okay, what test can we use now?
Comparison test.
Not just comparison test.
Comparison to the harmonic series.
It's the limit comparison test. See, the problem is that if you use just the comparison test, then the problem is that 1 over 5n plus 2 is smaller than 1 over n. So the comparison test doesn't work. The limit comparison test works. Does that make sense? So
yeah.
The comparison test is what we want to use. So we can use the limit comparison test comparing with the harmonic series. I'm just going to write 1 over n, which diverges by the harmonic series test. Any questions so far? And note that the limit, so let's copy paste. The limit of 1 over 5n plus 2 divided by 1 over n, which is the same thing as times n. And I'll just write n over 1. Oops. Is equal to what? What is that limit? Yeah, that's 1/5. Okay. And the important thing about 1/5 is 1/5 is not equal to 0. Because that's usually what you want to look at. You want a non-zero number if you can get one. So let me get to, there it is, not equal to 0. So we know this is not equal to 0. So oops. Oh, that's right, doesn't allow spaces. I have to do that, space, back, space, there we go. So by the limit comparison test, the series diverges. All right, what's the conclusion?
The interval is a square bracket of 2, comma 4, and then regular parentheses.
Exactly. So the interval of convergence is bracket, square bracket 4, comma, sorry, square bracket 2, comma 4, and parentheses. Any questions at all on this question? Okay, let's go to the second one. Okay, second one should be a bit quicker. So write down the power series that corresponds to this function. Okay, so the key on this one is, what does it look like? And the hint is, it looks like the only thing that we know how to do today, at least. Wednesday will be totally different. In 2 words. Yeah, it's geometric series. So this is a geometric series, but it needs to be tweaked a bit. So we can write, so we have x over x plus 1. So we can say that x over x plus 1 is equal to x times 1 over 1 minus a negative x. And now it looks like a geometric series. So it's kind of massaging what you had to start with. I think it was a 1 plus x, so maybe I'll fix that so it looks prettier. All right, so now that's a geometric series. And a geometric series, we have a formula for. That's the whole point. It's the only one we know right now. So that's going to be x times the summation of negative x to the nth power. Any questions on that? That is equal to the summation of x times negative 1 to the nth power times x to the nth power. But that is equal to the summation of negative 1 to the nth times x to the n plus 1. And now we have it looking like a series, like a power series. Okay, any questions on that? Okay, and that goes from 0 to infinity. If you want me to put them in, you can. I can, but if it doesn't say, it always goes from 0 to infinity because that's standard. So just a note, by the way, in hardcore physics, they don't even put the sigma in. Do you know who the they is?
Einstein.
Physics.
Yeah, Einstein. So if you read Einstein's original work, he's like, well, everyone understands. That's what happens when someone's much of a genius. And then you have to read through it, and it became somewhat normal, actually. So he doesn't even bother with a sigma because he said that's just too much writing. So I'm kind of like, I'm not Einstein, that's for sure. But I know math, so I could drop the n equals 0 to infinity. Any questions on that? Okay, that's the quiz. So any questions about anything that I went over or you've been working on or anything like that before I continue on? Any questions? Okay, so let's do the easiest part of the whole class today, and that is adding, subtracting, and multiplying by constants. Okay, so, okay, and I shouldn't say constants, non-series, I think might be a better word. So here's the good news. So let's just put in number 1. Is that if you have a summation, I am going to do things a little bit different than the book, just because I don't like the book's lettering. It's not wrong, it's just not as good. I'm going to use an x minus c to the n. And we're going to add this another one, bn times x minus c to the n. And we want to say, well, how do you add two series? Any questions on that? Make it a little bit, oh, won't let it be bigger. Now I can make it bigger. Let's try again. That's better. Okay, just to note, the book is kind of all over the place in lettering. They use CN and DN. And then they use later on C for the center, but here they don't use a center. I'm going to be using AN and BN because don't you think that makes the most sense? Like if you're going to pick your first two letters, A and B are better. But just if you go and read the book, it's going to be different letters. It doesn't change anything, but just want to give you a warning. So I feel that this is a lot easier to read this way. Maybe you agree, maybe you don't, but this is what I'm going to do. All right, so if everything was good in the world, how would you add these to make this? In fact, let me write this down. What I want to do is I want to write this as a single series instead of two series. How do you think you might do that? The hint is everything is good in the world. So what do you think you would do?
AN plus BN times x minus c to the power of n?
Yeah, it's exactly what you think that might be right. I hope you're all thinking that. There's nothing fancy here. AN plus BN, AN, AN plus BN, in parentheses times x minus c to the n. Okay, and I should say, suppose everything converges. Then you can do all this. If you have convergence, you know, it's the old thing, you can't just start doing infinity plus infinity. That's a mistake, okay? Or does not exist plus infinity is even like weirder. So we got to make sure everything converges. Is that clear? So if you have convergence, then it's what you expect. Any questions on that? Okay, well, here's the good news. Do you think you could take this same idea and do a subtraction? Do you think that'll work?
Yeah, why not?
Yeah, that still works. Okay, I'm not going to do a full proof of this. The true proof is a little messy. It seems like it's just obvious because you're just putting things together. But why do you have to be a little careful? We've seen this before in the alternating series test section. Right? Because what this does, 1 and 2, all it does is use the commutative property of addition. But what's the problem? Right, basically I rearranged all the parts. And you remember? Okay, the problem is, remember when you had the alternating series test, that the rearrangement theorem you can only rearrange when you have absolute convergence. But the good news is that when you have a power series absolutely converge as long as you're not at the boundaries. Okay, so as long as you're not at the boundaries, you're okay. Any questions on that? Okay. Turns out if you are at the boundaries, you're okay as long as you read from left to right, but you can't read from right to left. So there's some real kind of minor technical issues. The main thing is you can do what you want to do. Any questions on addition and subtraction? Okay, then there's scalar multiplication. And I'm going to do kind of a double scalar multiplication just for fun. And that is if you have some constant, how about k? And k is a good constant. And then some x to the, again, x to the, how about q? Just some letter. And then we take the summation of an x to the n. And you can replace the x with the x minus c. I'm a little bit kind of getting a little lazy here, but the book gets lazy too, so I don't feel so guilty. And it still works. Then if all things are good, what would this be?
Kx to the q times a n x.
So it'd be k, and then I'm going to do times an. I'm going to put the constants together and the x's together. So it'd be k a n. But then it would be x to the q plus n. Or let's go n plus q. Because the idea is that you can use the rules of exponents. X to the q times x to the n is x to the q plus n. It's a little more standard to write m plus q, so I'm writing it that way. Any questions on this? Again, the proof is subtle and kind of complex, and I don't think it's worth doing. If you guys really want to see it, y'all vote for it, I'll do it. But I don't think you'll get anything out of it, especially since we don't have a lot of math majors. I don't know if we have any math majors, but that's a math major kind of thing to do, not any other major. No other major would do it. But this allows us to take power series and kind of bring them together. Any questions on that? Any questions? Okay, maybe I'll do an example. The examples are pretty uninteresting, but just for fun, how about, I'm gonna keep it centered at the origin because it's just less typing. So let's suppose we had let's suppose we had 3 times the summation of 2 to the n, x to the n, and then plus 5 times the summation of, how about 7 to the n, x to the n. Okay, could you put this together in a single power series? The hope is you can, and the idea is it's not hard. So I'll start out. Summation. That's what you get. Gonna give you a moment. Shouldn't take too long. A little bit of typing, but not that much. I'll start out with a parenthesis. All right, maybe this is harder than I thought, but this isn't supposed to be that hard. I'll try. Okay, good try. You can't add the 3 and the 5 together because the 3 belongs to the 2 to the n, and the 5 belongs to the 7 to the n. So you can't merge the 3 and the 5 together. That's the only problem. So literally, there's very little to do here because you can't do much. Again, you should all be trying, not just the 1 or 2 that usually try, but everybody should try. It's always good for you, and you'll learn more too. I'll tell you my secret to doing well in my math classes is I was always trying to be 1 step ahead of the professor. And that way, if I didn't get it right, then I'd have my confusion answered when the professor did it. So it's good to try, even if you get it wrong. So let's see if you can all try. Okay, also a good try, but notice 3 times 2 to the n is not 6 to the n. Because the 3 doesn't have an n. And similarly, 5 times 7 to the n is not 35 to the n. So the key is there's very little math to do here. If you're doing any arithmetic, you're probably doing it wrong. That's a hint. So let's see, someone will get it right, because there's not much to do. Give you another minute. This isn't supposed to be brutal. Okay. Ralph, you're good, but you can also factor out the x to the n. So I think I'm going to go with that. So it's 3 times 2 to the n plus 5 times 7 to the n times x to the n. Any questions on that? There's no algebra you can do after that. That's it. A lot of you tried to do some algebra, but that's as far as you can go. And we now have a power series because we have some function of n, which is in here, times x to the n. And that's what a power series is. Any questions on that? Okay, so that was addition, subtraction, and I'm calling scalar multiplication because it's not, we're not multiplying two power series. On the other hand, what if we had to multiply two power series? Okay, so let me ask you, who remembers what FOIL is? You better all say yes.
First outer, inner, last.
Inner, last.
Good, and that's if you have like an a plus b times c plus d, right? Okay, what if you had 3 terms? Does that make it nice and fine and easy?
I mean, you can still do it. It's just more complex.
Exactly. You can still do it. It's just more complex. All right. So let's see what we got. And this time I'm going to put the numbers in because just to remind us. So we have a summation. I need some parentheses. So n equals 0. Super infinity. That was that one. Yep. Of a n x to the n. And then times the summation, n equals 0 to infinity. This time I'm putting it in to just emphasize that they're there, the 0 and the infinity, of Bn. Okay. So you kind of said it's a bit messier to do 3 by 3, right? What if you had 10 terms? And you had to multiply a 10 term by a 10 term? How many of you would volunteer right now to do that?
Definitely not me.
Okay, hopefully nobody. All right, now this is what you call health. Okay, so if you can imagine some horrible, torturous end of existence, if you had to do this, why would this be hell? What I have written out. How many terms are there?
Infinite.
Infinite. So now we got an infinity terms times an infinity terms. This is like an infinite FOIL. Sound fun?
No.
Okay. This would be hell. Do you agree? You can't do it. Doesn't mean it doesn't exist. Okay, it definitely exists in theory, but you can't do it. Is that clear?
Would this be something a computer would want to do?
Okay, a computer can't do it. Why can't a computer do it?
I don't think, now that I think about it, I don't know if computers know how to FOIL.
Oh yeah, computers can FOIL. I could program a FOIL in 5 minutes. But what's the problem? What can't computers do? It's not the FOIL, that's not the problem.
Deal with infinite values? I don't know.
Exactly, exactly. They can only do a finite number of tries, right? Of things. They can't handle infinity. So a computer can't do it, but here's what a computer can do. it can do the first maybe 20 or maybe 50. So it can go pretty far, but it can't go forever. Does that make sense? And in the real world, usually you only want the first maybe 20 or 50 or 100 or something like that. And then computers are good for that. So computers are very good for approximating this, okay, when it converges, okay? And if it doesn't converge, you have to tell a computer it doesn't converge. But they're good for that, okay? So this is a complete mess, this multiplication issue, okay? But it's useful if you're okay with an approximation where you don't go to infinity. Okay, do you think this ever happens in the real world
Yeah,
where you have to multiply?
sure.
Yeah, it does all the time. Okay, this is a biggie. And if you really want to do it, you need a computer. And what you do is you approximate it, you don't go off to infinity. And that's how you do it. I'm going to do a few of them. I'm not going to do what a computer could do, which would have million. But I'll do a few with an example. So again, I'm not writing down the formula because there is a long formula. I don't think it's worth learning the formula. I think it's better to understand how things work. So let me do an example. So I'm just going to do a copy and paste. And I'm going to change my AN and change my BN. So let's say AN is 2 to the N. And let's say BN is 1, will it let me do over? Oh, that's right. It's not having Canvas and Google, and I gotta remember which one's got which. So 1 over N. Sound good so far? Okay. By the way, when does this converge? When does this converge? Who could tell me when this converges? Just by looking at it. You know, there's a test you're going to use. A couple tests. Well, maybe one test.
When
test.
n is less than 1?
It's a good try. That doesn't quite work because if n is, say, 0.9, then you get 1.8 to the n for the first sum. You see that? Because 2 times 0.9 is 1.8.
Yeah.
So what do you want x to be less than in absolute value? To make things work.
.5.
Yeah, 0.5. Because 2 times 0.5 is 1. 1 to the n isn't okay. But anything less than 1 to the n is okay. So as long as the absolute value of x is less than 0.5, then this will converge. The first will converge, and the second one converges also, both by the ratio test, by the way. So that's just a note, is that 0.5 is the radius of convergence. Any questions on that? It's always good to explain, you know, remind ourselves. Okay, so the idea is now we want to multiply these guys. And the way you multiply these, I think the best way is expand them out one at a time. So let me do that. So this is equal to, well, 2 to the n, x to the n, n equals 0 to infinity. So it's going to start with a parenthesis 1 plus, so if n is 0, that's 1. Hopefully you all agree. Anything to 0 is 1 in our, even 0 to 0 is 1 in this particular, when you're doing series. And then if n is 1, you just get 2x. And then if n is 2, what do you get?
4x.
Close, 4x squared though, right?
Yes.
So 4x squared. And then if n is 3, you get
8x cubed.
8x cubed. And then I'm just going to go plus dot 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 because it goes forever and you can't do them all. Any questions on that? Okay, there are times when it is, I think, more helpful to write it out than to write it in Sigma notation. This is one of those times writing out is a little easier. Okay, so now we're going to do the same thing with the second series. So if n is 1, you get 1. 1 over 1 times x to the, sorry, if n is 0, you know what? I better not be 1 over n. That was a mistake. Plus 1. You have all kinds of problems when n equals 0 if you do that. So if n is 0, you get 1. If n is 1, I think I'm not. Oh, shit. I don't know how that plus got outside the equation. There we go. If n is 1, you get 1/2 x. If n is 2, you get 1/3 x squared. If n is 3, you get 1/4 x cubed. And I'm going to write plus dot dot dot. Any questions on that? Okay, so now what we're going to do is we're going to do the first few terms. There's no way we're going to get them all because that would be hell, remember? It would just be an infinite amount of work. So instead, we can get the first few though. Okay, a computer could get the first 1,000. We could do 2 or 3 until we like say, this is a pain, I'm going to quit. Okay, so what we're going to do now is we're going to say, imagine multiplying this out. What are you going to get for the term, the constant term, the term that doesn't have any x's in it? That's supposed to be really easy. That's a hint. Really easy. And sorry about this 1 over x cubed. I just noticed that got weirded out. That x cubed should be outside. That's better. So what are you going to get for the constant term? This isn't supposed to be hard. If you multiply this out, imagine multiplying it out. What are you going to get for the thing that doesn't have any x's in it? The constant piece.
1.
Yeah, it's just 1. Okay? Because all of the things with the x's in it will get you an x. The only way you're not going to get an x is to go 1 times 1. Remember, we're doing an infinite FOIL. So that's going to be 1. Okay, now what we want to do is we want to do the linear term. So notice that as soon as you have any of these higher order stuff, that will not even affect the linear term. So neither will these guys affect the linear term. Linear term means the term that's just an x. So in a way, we're foiling 1 plus 2x and 1 plus 1/2 x. Let me mute whoever's talking. Okay. So what are you going to get? Just 1 second. There we go. What are we going to get for the term with just an x in it? And again, what you're doing is you're kind of like foiling the first 2 terms with the first 2 terms of each. And you're thinking about what are you going to get with just an x? Because everything after x, all the x squareds and x cubes and stuff, don't matter.
5/2 x.
Yeah, because you're going to have a 2x plus 1/2 x, and that's 2.5 x. or 5/2 x? All right. I think I'll do the quadratic and then I'll realize that I don't want to spend any more time doing it. Okay. So now if you want to do the quadratic, now we got to FOIL. It's not really FOIL anymore. It's a much longer word. The first 3 terms by the first 3 terms and see how are you going to get x squareds out of them, right? Everything x cubed and beyond are unimportant when you're looking for just the x squared term, because you'll never get an x squared if you multiply by x cubed times some integer positive power of x. So how are you going to get an x squared? Well, we could do a 1 times a third x squared. You could do a 2x times a half x. That gives you an x squared. And you could do a 4x squared times 1. So 1 times a third is a third. 2 times a half is 1. So now we're at 1 1/3. And 4 times 1 is 4. So we're at 5 1/3, or 16/3. Okay. Just a note, it may feel like there's a pattern, right? But is there? Do you see a pattern?
No, not really.
Yeah, not a real easy visual pattern. And that's, oh, sorry, I forgot the square. And that's kind of how it always is, which makes it a pain in the rear, because pretty much to do the next one is going to be even messier. Do you agree?
Yes.
Okay, and then after that, you're going to say, I'm just going to use it. Okay? That's how you do it. Okay, but it's important that you understand it. I could ask you the first couple terms, and that's something you can do. I wouldn't ask you the first time. That'd be evil. But I want you to understand that this can be done. This is how it's done. It's done by cutoff foiling, kind of cutoff multiplication. You say we want to get it to that power, so at that power, cut off everything beyond that power, multiply through, and see how you get to that power. Have I lost you guys, or do you understand what just happened? I'm gonna write plus ...
I am a little lost on how you got the 16/3. So essentially what you did is you multiplied.
Yeah, so I went 1
Mhm.
times a third.
Okay. Which
That's
is
a
1/3.
third.
Yep.
Let's write this out. 1/3, 1/3. So we have 1/3. I did it in my head, so I could have made a mistake, but I think I got it right. And now let's do the 2. Well, we're gonna have a 2x times a half x.
Which is x.
Right, or 1x.
Or 1. Yeah.
Right, because we're only looking at the coefficients, because we know we're gonna have x. It's x squared, not x, by the way.
Okay.
We know we're gonna have x squared when we're done. Do you see that?
Yeah.
Okay, then we're gonna say 4 times 1, because that'll get you an x squared, right?
4.
So plus 4.
Okay.
And that is equal to 5 1/3.
Yes. And then plus 1/3.
And now I just
Got
took
it.
the mixed fraction and turned it into an improper fraction.
Yeah, I just did it in my head. Okay, that makes sense.
Improper fractions are dangerous when it comes to typing and stuff. Sorry, yeah, mixed fractions are dangerous is what I meant. Okay, and again, I did do the x cubed term because if you thought the x squared was kind of messy, it just gets worse and worse exponentially. It's just horrible. Okay, any questions on this example? Okay, as bad as this example is, now think about the next operation that you do in terms of arithmetic. We just did addition, subtraction, multiplication. What's next?
Division.
Division, okay? And these are polynomials, right? But they're infinite polynomials, right? The power series. So now go back to your, intermediate algebra or college algebra and think about, adding polynomials, not too hard, subtracting, not so bad. You got to deal with the minus signs. Multiplication, pain in the butt, right? How about division of polynomials? Do you like that?
It's not the worst thing ever, but
Really?
yeah.
Try with power series. I think you'll change your mind. It is the worst thing ever. If you have to divide two power series, it's infinite long division. You sure it's not the worst thing ever? Okay. Even polynomials, if you had to do a 5th degree polynomial divided by, another bit, like another third degree polynomial, it's a pain. It's a lot harder than multiplication. But so I'm not gonna, spend time doing it, but I will tell you that you can divide power series. And the way you do that, let's suppose, I'm gonna do the following. I'm just gonna kind of show you the idea. I'm not gonna do it, it'll take too long. Instead of multiplying, let's say we want to divide. Okay, so it turns out long division is not the way to go. What you do instead is you go to the definition of division. And that is, I think I'll do X, Y, and Z. I think it's easier to understand. If you have X divided by Y, equals Z, then how do you turn that into multiplication?
Y to the -1 power.
The problem with that is we don't know what exponents are.
Okay.
So now you got to go back to 3rd grade. I know it's been a few years for all of you. Is how did you define division? When you first learned how to divide nice numbers.
How many times something goes into something else?
Exactly. You turn it into a multiplication problem. You do it into a times. And you say that X is equal to ZY. You could do YZ, but it turns out ZY is a little easier in this for our case. Any questions on that? Okay, so if you have X equals ZY, in our case, what we can do is we can pop in a new one and say, well, we don't know what it is, but we do know that it is the summation of, how about C and X to the N? So now what we can do is we can rewrite it. We can rewrite it as kind of a questioning thing. So we can say X, which is 1 plus 2X plus 4X squared and I could do the next one. I think I can go dot, dot, dot to save time. Plus dot, dot, dot times, oh, sorry, that was, I don't want X, I want Y. So I want ZY is what I really want. Sorry about that. So here we're going to have ZY. So our Z is CNX to the N. I can just copy that guy. Actually, I don't want to copy. I want to put an equation. So Cn now is going to be C1 plus C naught is what I want, plus C1x plus C2x squared plus dot, 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 and then times 1 plus a half x plus 1/3 x squared plus dot, dot, dot. And that is equal to, and now we can write down what it equals, which is 1 plus 2x plus 4x squared. Plus dot, dot, dot. Any questions on what I just did? Okay, so now what we do is we say, well, what is C naught? So can you tell me what C naught is? Just by looking at this equation that I have.
1.
Yeah, C naught is 1 because we need C naught times 1 equals 1, so C naught is 1. So let's do that. C naught is equal to 1. How do I get C1? Well, I know C naught is 1. So 1 times a half plus C1 times 1 is 2. So a half plus C1 is 2. So C1 is 3/2. And again, I don't have so much time, so I think I want to stop there. You could do C2, you could do C3. Those who know some computer programming, what do you call this way of doing things? Starts with an R. Maybe no one knows computer programming, and that's huh?
Recursive.
Yeah, this is called a recursive algorithm because what we're doing is we're using the prior one to get the next one. So we use the C naught equals 1 to find C1. And then to find C2, you're going to use C naught and C1 that you know to find C2. And then you just keep going forever. Or not forever, but for as long as you get tired. Okay, and if it's a computer, as long as the computer gets tired. Because computers will start spinning after a while too if you ask it to do a trillion of them. Okay, because these are forever. Any questions on the idea of multiplication and division? Okay, hopefully you agree these are hard in terms of like messy hard. Once you do a few of them, they're at least theoretically they're not bad, but they're really messy, awful fractions. Okay. Now we're going to be doing a big, gigantic jump forward from 3rd grade math to this year. I'm going to do calculus. And the funny thing is 3rd grade math is much harder for what we're doing. Okay. This whole recursive, division stuff, that's a pain. Turns out calculus is really simple. So let me talk about it. This is a theorem. And it's a really important theorem. It's the whole point of why we care about this. And that is let summation of an. Oh, you know what? I need the numbers here. N equals 0 to infinity. of a sub n, x to the n. And you can do x minus c if you want, but it's just less writing to do x to the n. But I'll let you imagine the x minus c be a power series. And actually, let me, just to make it look better, and call that f of x. Then it'll feel more like calculus. Then okay, what I want to do now is I want to do calculus. So what's an important thing to be doing? If you have a function and you want to think calculus, what do you want to do?
I want to differentiate or integrate.
Exactly. Actually, I'm gonna correct you a bit. Want to differentiate and integrate. Sound even better? Let's get greedy. Okay. So let's start with differentiating. Well, think about it. A power series is just a big fat polynomial. Do all agree? How do you differentiate? I don't even have to, like I said, I'm going to write down the theorem, but I bet you could write down the theorem without me even saying anything. How do you take a derivative of this? I'll start out at prime of x. Well, how do you take a derivative of an addition, big addition problem of a constant times x to the n?
Power rule.
So it's just a basic power rule. And power rule says the derivative of a constant times x to the n is the constant times n times x to the n minus 1. But there's one problem. What's the one problem? Why is this wrong? It's a subtle piece, but it's wrong. And the hint is, I didn't get lazy this time and just write sigma. I wrote n equals 0 to infinity. Anyone see the problem? Okay, the problem is you want to start at 1, not 0, because the constant term goes away. Otherwise, you're going to have an x to the negative first power. You have all kinds of problems when x equals 0. It's just going to be bad. So you usually want to start at 1 when you have a derivative. Okay, does that make sense? Because the constant term is gone. So we don't even want to even think about a sub 0. We're going to think a sub 1. Any questions on that? I think I'll call this number 1.
Yes, I have a question. Does it have to be convergent or can they diverge?
Well, if it diverges, what's the derivative of something that does not exist?
It doesn't exist.
Yeah, so it doesn't even make any sense if it's divergent. Does it make sense?
Yep, sounds good.
Yeah. So that this just assumes if it's divergence, you don't even talk about it. Right? Is that clear? So yeah, if it definitely has to be convergent. Okay. Here's number 2. Again, we can get greedy because you said, or someone said, we want to either differentiate or integrate. I want to do both. And the nice thing, this is like beautiful. Remember how long it took us to just learn how to do some of the integrals in the world? It took an entire quarter, didn't it?
Yeah.
But for power series, it takes 10 seconds. So again, I'm going to copy that guy. And I want to take not f of x, I want the integral. That one. Yeah. Oh, I know. I think I do that and I don't put anything in. Whoa. That made it look weird. But that's what I got to do, I guess. I think. Yeah. So I'm going to have the integral of f of x dx. And here's the wonderful thing. Power series are polynomials. Polynomials are like some of the easiest things in the world to take an integral of. How do you integrate a n x to the n, a constant times x to the n power?
N plus 1 divided by n plus 1.
I think you got the right idea. You're just saying a little weird. It's x to the n plus 1. And then we're going to divide by n plus 1. So it's going to be an will be the numerator, and then n plus 1 will be the denominator. Is that correct? And here's a hint. You got to think about what you learned last quarter.
It can't be n equals 0. It has to be n equals 1.
No, n equals 0 works here. Because the interval constant is an x to the 1. So that works. Here's a hint. If this is what you wrote last quarter, I'm going to take 1 point off.
Plus c.
Yeah, plus c. Okay, and it's a little more common to do a c plus, and the reason for that is that the c is not really inside the summation, and that pulls it out. Otherwise, you could use parentheses and stuff. So it's really easier to do it this way. And I don't know why it's doing these high and low stuff. Infinity's way up, but that's just Google. Okay, any questions at all on this? Isn't this beautiful? So integration is nothing. You don't have to know you don't have to know anything about last quarter, basically, other than the power rule, and you can integrate every power series. Isn't that wonderful? Okay, and differentiation is also easy. You don't have to memorize, the derivative, the arctangent of something or whatever. They're just polynomials. Okay, now, one of the things you might want to think about is, what about convergence? So the key on this is you look to see what happened when we took a derivative. When we took a derivative and now you look at the term, did it get bigger or smaller? So kind of compare the f of x to the f prime of x in terms of what's inside the summation.
Depending on the constant, in front of the variable, it got bigger when you differentiate.
It actually doesn't depend on the constant. It got bigger because we multiplied by n, right? N goes to infinity, right? And we got rid of an x, but x is just a number, right? So we're multiplying, you're taking infinity times a number, and that's what we're multiplying by. So we actually are making the inside or the terms bigger when we take a derivative. Do you see that? So you can't lose you can't lose divergence. Okay, on the other hand, we only made it bigger by a multiple of n. And remember, step 1 on checking for interval of convergence is ratio test. And the x to the n, or the x to the n minus 1, those are going to be what counts most on the ratio test. So the radius of convergence will stay the same. What might happen is you might lose an endpoint. Okay, so your square bracket might turn into a curly bracket or a curly parenthesis. Does that make sense? Okay, but as long as you're inside the interval and not on the boundary, you stay convergent. But the boundary could be lost. What about the integral? What's bigger? The integral or the original?
I think they might be proportional.
Not quite. was a good try. So look at it. The difference is the 1 over n plus 1. N's infinity, remember. N goes to infinity. So now take a look. What's bigger? The f or the integral?
The f.
Yeah, the f is bigger. So in that case, we got something smaller. So by the direct comparison test, if f converged, so does the integral of f. And but the point is the x to the n is the dominant term. So when you do the ratio test, this dividing by n plus 1 doesn't change anything. So again, the radius of convergence stays the same. What might change now is the endpoints, and you might gain endpoints. So an integral might turn a parenthesis into a bracket. A derivative might turn a bracket into a parenthesis. But the endpoints are always the same. It doesn't change the radius of convergence, or the center, of course, doesn't change. Let's write that out. So if the radius of convergence of f of x, convergence of f of x is r, then the radius of both the derivative and the integral are also r. Okay. The derivative can, but not always, take an endpoint that converges and make it diverge. The integral can, but not always, take an endpoint that diverges and make it diverge. Otherwise, the endpoints stay the same. So let's say the endpoint divergence or convergence stay the same. Any questions on that idea? Okay. One of the nice things is we can do an example that's not too bad. What if we find the series for f of x is equal to natural log of 1 plus x. Okay, now that you look at that and you go, I have no idea, right? I don't know if that's what you're all thinking. But there's something we can do. It's a trick. Thinking about what this whole last theorem. What can I do to both sides? Any ideas? Thinking about what I've just been talking about. I don't see you answering, and we don't have much time left, so I think I'll tell you. You could take a derivative of both sides. Okay, what we can say, and I hope you all remember how to take derivatives, f prime of x is equal to 1 over 1 plus x. Any questions on that? But 1 over 1 plus x, we can write a series for. Why can we write a series for 1 over 1 plus x? Any thoughts? I don't see y'all jumping in. It's not hard. It's a geometric series. And in this case, it's 1 over 1 minus negative x. So it's just going to be negative 1, or it's negative x to the n power. Any questions on that? Which, by the way, is equal to the summation of negative 1 to the n times x to the n. All right, we're not done yet, because I want the series for f of x, and I have the series for f prime of x. So how do I get the series for f of x? Don't see y'all jumping in. We don't have much time. Just waiting. Okay, well, if you know f prime, yeah, we integrate. If you know f prime and you want f, you integrate. So I'm going to integrate, and I get f of x when I integrate. And now I can integrate the series really easily. That's just going to be the summation of negative 1 to the n times, actually I need to use the formula, so I need to divide it by. So negative 1 to the n divided by n plus 1 times x to the n plus 1. And then plus c, or c plus. And there's my function. And what I'm not going to do right now today, but we will later on in a couple days, is we'll talk about how do you find the c, because the c does exist, because we know that f of 0 is 0. Natural log 1 is 0. So c should make the 0 when you plug in 0. Okay, and if you sit there and look at it, you'll realize that since we have an x to the n plus 1, that just gives you 0 if you plug in x. So the c is gone. But you always have to think about the c. And there's our series expansion for natural log of 1 plus x. Okay, we're about out of time, but I want to just mention, it's on my agenda. I'm just going to say it, I told you it quick. Uniqueness, and that just says that that if you have two functions that have the same power series, then they must be the same power series. The an and the bn's must be the same if they're the same function. That's all that is that there's a unique way of writing a function as a power series. But on Wednesday is the big day, by the way. I should let you know that. Wednesday is the day where we actually make use of this stuff. And all of a sudden you're going to say, wow, this, power series does everything. We don't see that yet, but you will on Wednesday, I promise. So it's a big, big deal. Wednesday is the big day of the entire quarter in terms of important, useful material. So hopefully you'll be here Wednesday.
I just want to be clear. You said uniqueness is if two power series are the same, it's the same function. They are the same function.
Yeah, and vice versa. So in other words, If you have a function and you want to represent the function as a power series, there's only one way of doing it.
Gotcha.
If you change, you can't change the constants around, it doesn't work. Does that make sense?
Yeah.
That's all that says.
Cool.
So it's not that deep.
Okay.
Whereas Derrida's integrals, I want to spend my time on that because those are important. They're
That's
hard, but they're deep and important. Okay, so we're out of time, so I'm going to stop the recording.